All right, so this is chapter 16, redox reactions or oxidation reduction, part 2. All right, so we're going to balance redox reactions. And redox reactions occur in aqueous solutions, so they occur in water and are usually difficult to balance by inspection. And they require a special procedure called the half reaction method. In this procedure, the overall equation is broken down into two half reactions. So one's for oxidation and one is for reduction. And in the textbooks, they say you have to figure out which one's being oxidized and which one's being reduced first. You don't. You just look at similar atoms and pull it apart that way. The half reactions are balanced individually, and then we add them back together. So let's look at how this is done. And so before now, you've always just looked at chemical reactions and you've said, okay, I have one aluminum on the left, one aluminum on the right, so that's balanced. But in reality, you've never seen a redox reaction because you've never been given one. Or you've never been given one like this. So this all added together, if this aluminum is 0 and this is +1, then over on the left-hand side of the reaction, the reactant side, there's a +1 charge overall. And then on the product side, I have +3 and a 0. And so that would be +3. So the charges aren't balanced. And that means the reaction isn't balanced. So not only do you have to have mass balanced on both sides, have the atoms balanced on both sides, but you have to have the charges balanced as well. And so I'm going to show you, you might want to write this down, but you might want to wait until the page where I have them all on there with acid-base solutions too. But by writing it down or writing part of it down, you'll be able to follow me on the next slide. I'm going to go ahead and show you this on this slide first. Hopefully I don't run out of room. So I have aluminum going to aluminum +3. So I just picked the two atoms that were the same and put them in their own half reaction together. And then I have silver +1 going to just plain silver. The atoms of aluminum are balanced here, so I did this first part. I'm going to balance atoms other than hydrogen and oxygen in both half reactions. So the atoms are balanced. I have one aluminum on each side and one silver on each side. And then I'm going to add electrons to the half reactions to balance them by themselves. So what that means is I've got +3 charge here, and I've got a 0 charge on this side. So I have to bring them down by adding electrons. So I'm going to add 3 electrons to the product side of aluminum. Now, this side over here is 0 because I have 3 positives plus 3 negatives, and so that's 0. And then this side over here is 0. And so those charges are balanced in that half reaction. Now I'm going to do the same thing on the bottom, but I'm going to have to add an electron to the left-hand side of the silver, because if I have one electron and 1 + 1, that means that it's 0 here, and it is also 0 here. So now that my half reactions have balanced charges, I'm going to look at them. And real quick, I'm just going to explain a concept. And you don't have to do this when you're balancing these reactions, but this right here is being oxidized. It's going up in charge. It's also spitting out electrons. And so that means that it's losing electrons, and this is taking in electrons. So that means that it's being reduced. So if the electrons are on the reactant side, then that means it's being reduced. The electrons are on the reactant side, that means that it's being reduced. All right, so now if I spit out 3 electrons, this reaction on the bottom half reaction, the silver half reaction, will have to happen 3 times. And so that's what this means. Multiply half reactions by a factor to make the electrons cancel out. So if I have 3 electrons leaving aluminum, then 3 electrons have to be taken in here. But since it's balanced, I have to put that 3 to the whole reaction. So that means that I would write it 3 electrons plus 3 silver ions gives me 3 silver atoms. And then when I add these reactions back together again, the 3 electrons will cancel out because I have 3 electrons being put out, 3 electrons being put in. So those electrons always have to cancel out when you add them back together. So I have aluminum plus the silver, 3 silver ions, goes to 3 silver atoms, plus aluminum 3 plus. So now when I look at the charges, on the reactant side, I have 0 on the aluminum, and then I have 3 pluses, so that would be plus 3. And then I have 0 here for this silver and plus 3 for this aluminum. So now my charges are balanced, and I'm just going to check to make sure that my charges are balanced on both sides before I say, okay, this is my reaction is correct. All right, so let's do another simple one like that before we get to the harder stuff. All right, this reaction is already balanced, so I'm going to change it so that it's not. This should be 3 plus here. All right, so we have Fe3 plus going to Fe, and then magnesium goes to magnesium ion. So those are my two half reactions. Now if I want to make this balanced here, remember this is 0 and this is 3 positive, and it has to be the same charge on both sides. So I can only add electrons. You can't add positives, you can't add protons. That's not how this works. So we have 3 electrons going in, and then we have magnesium going to magnesium 2 plus, so there has to be 2 electrons here. Now, I have to multiply by a factor that will make those electrons cancel out. So if I have 3 electrons here and 2 electrons here, the common factor between those two, or the common multiple between those two is the proper way to say it, is a 6. So I'm going to multiply this one by 2 and multiply this one by 3 to give me 6 electrons on both sides so that those electrons will cancel out. So that means that I would have 6 electrons, and then I would have 2 iron 3s and 2 iron atoms. And here I would have 6 electrons, and then 3 magnesiums and 3 magnesium ions. So that when I added them back together, the 6 electrons on both sides would cancel out, and I would have 2 Fe3 plus 3 magnesiums give me 2 Fe atoms plus 3 magnesium 2 plus. And so one thing that you can remember is that if it's just a plain atom, it's going to be a solid, and if it's an ion, it's going to be aqueous. So you don't have to always keep looking back. All right, so now if I want to check my charges over here, the 3 magnesium zeros would be 0, and then we have 2 Fe3 plus, and so that would be 6 plus over here. And then on this side, I have 6 plus and 0, and so the charges are balanced, and so that would be my balanced reaction. All right, so balancing in acidic and basic solutions. This is a little tougher. And I won't really go crazy with this on you, but you should see the half reactions at least with the acid stuff. But I am going to teach you how to do it all. All right, so what I would do is pause this and copy these down. This is very important. Unless you have a printer and you can print it out. Sorry, guys that don't. I try to make it as easy as possible, but that's the only way that we can do this. And then I'm going to show you, I'll have 3 examples, 2 in acids and 1 in base. All right. So balance the following reaction in an acidic solution. So first I'm going to break it down into half reactions. So I'm going to put this as my first half reaction. And then this one will be my second half reaction. And the first thing I'm going to do is make sure that my atoms other than hydrogen and oxygen are balanced. And here they are. We have 1 chlorine and 1 chlorine and 1 sulfur and 1 sulfur. So that part is good. And then next I'm going to balance my oxygens with water. So I have 3 oxygens here. So that means I'm going to add 3 water molecules to this. And then I'm going to balance my hydrogen with H plus because that's what an acid is. So I will balance my hydrogen with H plus. There's 6 hydrogen here, so I'm going to put 6 H plus there. All right, and then on the bottom half reaction, I'm going to do the same thing. So I have 2 oxygen here and 4 oxygen here, so that means I need 2 waters. That would give me 2 oxygen here and 2 oxygen here, so 4 oxygen total. And then I have 2 waters, and so that means that I have 4 hydrogen altogether. So I'm going to add 4H plus. Now the reason we do that before we do the electrons is because that H plus changes the charge on the side of the reaction. So on the top, all together, I have plus 5 because I have 6 positives and 1 negative, so that's plus 5. And then on the reactant side, I have -1. So that means that I have to bring down one side. I can't bring one side up, I have to bring down one side. So if I add 6 electrons to this, 6 negatives plus 5 positives would give me a -1 charge on the reactant side. And so that means that it would be balanced in terms of charges. So you don't have to get them to 0, you just have to get them to the same charge on both sides. And then on this one on the bottom, we have a -2 and a +4, and so that would be +2, and then over here is 0. Now I want them to be the same, and so I have to bring the bigger side down. You always bring the bigger side down. And so I'd have to add 2 electrons to this side. Looking at this, I have 6 electrons coming in, so that's the reduction reaction, and 2 electrons coming out. So that means this happens 3 times for every 1 time this happens. So we have to balance that. So this would be 6, 3, 3, 12, and 6. So then I'm going to add these reactions together. So the 6 electrons would cancel out. And I have 6 hydrogen ions here and 12 hydrogen ions here. So I'm only going to put the 6 hydrogen ions on this side because they're going to cancel out if they're on opposite sides of each other. And then we have 3 waters and 6 waters, so those 3 waters will cancel out and we'll get 3 waters left behind here. So then when I add them all together, I get 3H2O plus chlorate plus 3 SO2s goes to chloride plus 3 sulfates plus 6 hydrogen ions. And you could check all the atoms and make sure they're all balanced, but usually what I check is if the charges are still balanced and the hydrogens are still balanced, then you get it pretty good. It's pretty good balanced, okay? So first I'm going to check my charges. So over here would be -1, and I've got -6 for sulfate, -1 for chloride, and +6, so that would be -1 overall. So the charges are balanced. And then checking my hydrogen, I've got 6 hydrogen here, 6 hydrogen on the right side, and so my hydrogen is balanced. And so this is balanced in acid. All right, so I'm going to do the same thing here. I've got MnO4 minus going to Mn2 plus, and then I have CH3OH going to HCOOH. Okay, so in the first reaction, my manganese is balanced. So I'm going to go on to the oxygens, and I've got 4 oxygens over there, so I need 4 waters. And then that would be 8 hydrogen, so I need 8 hydrogen ions here for the acid part of the solution. All right, my carbon is balanced, and then I'm going to go to my oxygen, and my oxygen is 1 on the left side, 2 on the right side, so that means that I'm going to need 1 water over here. Now I've got 2 hydrogen here and 4 hydrogen here, so that's 6 hydrogen, and I've already got 2 accounted for right here, so I'm going to add 4 hydrogens to that side. So now with the electrons, I need 4 electrons on the bottom reaction. I just happened to see that. So this is 4 plus, and this is 0. And then up here on the top, we have 7 positives and +2. So that means that I'm going to have to add 5 electrons to this side because I have to bring the big side down to the lower side. So I have 5 electrons and 4 electrons. So the common factor between those two is 20. So I'm going to multiply this top reaction by 4 and the bottom reaction by 5. So a lot of the time I would rewrite these. So 20 electrons, 32 hydrogen, 4 permanganates, 4 manganese 2 plus, and 16 waters. So that's been distributed. And then I've got 5 waters plus 5 methanols goes to 5 formic acid plus 20 hydrogen plus 20 electrons. So then I'm going to add the purple ones back together and cancel out what occurs on both sides. So I have the 20 electrons will cancel. And then I've got 16 waters here and 5 waters here. So that means that these 5 will cancel out, but I'll have 11 left. And then for my hydrogen, I've got 32 hydrogen here. I've got 32 hydrogen here and 20 hydrogen here. So that means that there's going to be 12 hydrogen left over on the top here. So then if I write all this down, I would have 12 hydrogen plus 4 permanganate plus 5 CH3OHs plus 4 manganese, 11 waters plus 5 HCOOHs. So now I'm going to check my charges first. So this would be 12 positives and 4 negatives is 8 positives. And then over here on this side, I have 4 plus 2s, so that'd be 8 positive. And then I have 12 hydrogen plus 20 hydrogen in this one. So that would be 32 hydrogen total. And then I've got 11 water, so that's 22 H's plus 2 H's in every single one of those, and there's 5, so that means 10, so that's 32 hydrogens. So this is balanced. All right, so this reaction doesn't work well for basic solutions for demonstrating what I want to show you, so I'm just going to make a new one up. I'm going to say if I break it down into half reactions, I have manganese 2 plus and permanganate, and then I would have dichromate to chromium. All right, so I'm going to balance this in basic solution, and the way that I do that is different than your book tells you. I wait to make it basic until the very end of the balancing process. They do it in the middle of the process, which I think creates more places for error. So everything I do up until the very, very end will be the same as it would be if it was in an acidic solution. So first I'm going to check to make sure my atoms are balanced, and the manganese is balanced, but the chromium in the second reaction is not. So I need 2 chromium 2s to balance out the Cr2O7. Then I can balance my oxygen with water and my hydrogens with H+. So since I have 4 oxygen on the product side, I'm going to have to add 4 waters to the reactant side. And since I have 4 waters, that means I have to add 8 H+ to the product side here. And in the bottom reaction, since I have 7 oxygen, I'm going to have to add 7 waters to the bottom here and 14 hydrogen to the left-hand side. All right, so now for my charges for electrons, I've got 2 plus here and I've got 7 plus here. So that means I'm going to have to add 5 electrons to the product side of the first half reaction. And then I have 4 plus on this side, the product side of the bottom reaction, and 12 plus on the reactant side. So that means that I'm going to have to add 8 electrons to the reactant side here. All right, so now I'm going to have to find a common factor, and that would be 40. So I'm going to multiply this top reaction by 8 and multiply this bottom reaction by 5. And I'm going to rewrite those down here. So if I distribute 8 across all of these, so I'd have 32 waters from the top reaction, 8 manganese, 8 permanganates, 64 hydrogen, and 40 electrons. And I'm going to do the same thing to the bottom reaction. So I'd have 40 electrons plus 70 hydrogen plus 5 dichromates plus 10 chromiums plus 35 waters. All right, and then I'm going to add the reactions back together again, canceling out what occurs on both sides. So if it's a product and a reactant, then it cancels out. So I have 40 electrons canceling, and then these 32 waters would cancel and leave me with 3 on the product side. And then 64 hydrogen and 70 hydrogen would leave me with 6 hydrogen. And so now I'm going to add those together, and I've got 8 manganese 2 plus 6H plus 5 dichromates gives me 8 permanganates plus 10 chromium 2 plus 3. Okay, so now I'm going to check to see if my charges are balanced and my hydrogens are balanced. So I have 6H pluses here and I have 6 H's here, so that's balanced. And then I have 16 plus 6 minus 10 would be 12. And I have 8 plus 20, negative 8 plus 20 is 12. So my charges are balanced and my hydrogens are balanced. So what about the basic part of this? Because right now it's an acid. So bases are made from OH. And so since I have this an acid, if I add 6 OHs to this, then that means that I make 6 H2Os. But since it was already balanced, I've got to add those 6 OHs to the product side as well. So I'm going to add 6 OHs to the product side. And so this would make 6 waters, and I've got 3 waters here, so those 3 waters would cancel out, and I'd have 3 waters left over. So now if I rewrite this, it would be 8 manganese plus 3 waters plus 5 dichromates goes to 8 permanganate plus 10 chromium 2 plus 6 OHs. So I'm going to check one more time to make sure that it's balanced by counting my hydrogen and charges. So I have 16 pluses plus 10 negatives, and so that is going to be 6 plus. And then over here I have 8 negatives plus 20 positives plus 6 negatives, and so that is going to be 6 positive. And so that balances, and then my hydrogen, I've got 6 here, and I've got 6 here, so that balances. So this would be now balanced in a basic solution because it has OH in it instead of H. So you just add enough OHs to cancel out your H's, make those into waters, and then add the OHs to the other side as well to make sure that you keep it balanced.